Hello and welcome back. Today we're looking at frictional forces and efficiency. Designers of mechanical devices often discover what seems to work in somebody's head. The head doesn't always work in reality. Sometimes things as simple as a breeze of wind can change what happens with the product. Ah! Oh! Oh! Oh no! Oh! And sometimes something as simple as a drop of water can change everything that we've done and how the machine actually works. Two component parts of a machine could rub together on each other, causing the device to no longer function. Mechanical efficiency is a measure of how well a machine uses energy. It is important to know because it helps you decide whether the amount of energy you have to put into it is worth what you get out of it. Friction can have an enormous effect on efficiency. Think about the different efforts needed to push this heavy table a few meters compared to if I put little wheels on the bottom. Friction is the amount of force working against the machine or against the direction of work. Friction between a heavy block and the ground is much greater than friction between rotating wheels and the ground. Efficiency is often described in percentages. If no energy was ever wasted in using a machine, it would have an efficiency of 100%. But no machine is really 100% efficient. Some energy is lost. When using a machine, the work output is always less than the work input. However, machines do still change the effort put in, and that can still be important. Efficiency is also a comparison of mechanical advantage, the added force of using the machine, with the speed ratio, so how far you get compared to how hard you work. Here's the formula up here in the corner. Okay, so if I have a pulley system and it uses an input force of 3 newtons and achieves an output force of 6 newtons, someone using the pulley system will pull the rope 12 meters in order to lift the load 4 meters. What is the efficiency of that pulley system? Well, the first step is to find the mechanical advantage and the speed ratio. So how do we do that? So I have my load force, and I know my load force is 6 newtons. Right? Newtons is force, so we always know. And I'm going to divide that by the effort force, which is 3 newtons. And that I got that information from here. Okay? And then that is going to equal 2. Okay, so that is my mechanical advantage. And then I'm going to find the speed ratio. And the input distance is 12 meters. And the output distance is 4 meters because the rope was 12 meters and it lifted the load 4 meters. And that ends in a speed ratio of 3. Okay, so now I'm looking for efficiency. So I take the mechanical advantage, which is 3, and the speed ratio, 2, and the speed ratio, which is 3, and I plug that into this formula here, times 100, right? And then I have, that's 0.6, so I'm going to round it to 7 here. So it would be 6, 6, 7. That's here. I'm going to multiply that by 100. And that is going to equal 66.7%. Okay, the pulley system uses 66.7% of the energy put into it in order to do the work. So here is another way to look at it, though. The work done on this pulley machine is equal to the work done by the pulley machine. Okay, so the 66.7% plus the energy lost due to friction, heat, or slippage. So that is 33.3% is what is lost due to those things. The chain on a bike might have oil on its surface. The oil is going to act like a lubricant to reduce that friction between the gears and the chain. So that is when we reduce the energy that's lost and boost the energy that's used to perform the work. So in the example with the pulley, if I put oil or water on the rope, it might make it easier to pull the rope and then therefore reduce the energy needed and make it more efficient.